Hello friends, welcome back to the tetrahedral chemistry classes. So guys, in today's lecture I am going to discuss the Wolff rearrangement, and the reaction is there in the syllabi of your IIT JAM. Okay, and but this reaction is equally important for your other competitive examinations as well. Okay, so what is actually Wolff rearrangement? It is nothing. You will take your alpha diazoketone, and if you subject this alpha diazoketone to heat or subject to light, or if you take some sodium 1 salt, right, you may also take the rhodium 1 catalyst, then this alpha diazoketone will convert into the ketene. Okay, so ketene, just you can consider, if you know the formula for the ketone, so you simply put one extra double bond to get the ketene. So it is just like the sister of the ketone. Okay, and of course the nitrogen gas would remove in that case, which will increase the entropy of the system, and this is actually the driving force for the reaction. So whatever actually what I have said, actually you can summarize in the particular reaction. So how we can write the reaction? Say this is your R, and this is the C double bond O, and then you are having CHNH2. Okay, so you are having this species, and that is species, not NH2, sorry, it is not NH2, it is N2. Okay, N2. So this is your alpha diazoketone. Okay, so why alpha diazoketone? In that case, you can see here, this is your principal carbon, and this is your carbonyl group. This is the main functional group, and that carbon which is having which is the alpha carbon, and that alpha carbon is having two nitrogen, two substitution of the two nitrogen. That mean it is diazo, and it is a ketone, so it is alpha diazoketone. So what you can do, you can subject this alpha diazoketone to any of the reagents. Usually this reaction is done with the help of the sunlight, but you may also heat the solution. Either you may heat the solution, or you can actually shine light on it, and sometimes you can also take some sodium 1 salts. Okay, and rhodium 1 catalyst are also used in that case. So these are the possible reagents for this one. So when you do this reaction, then it immediately converts into your ketene. So the formula for the ketene is what? RCH double bond C double bond O, and this nitrogen will remove from here as a gas, and this will increase the entropy of the system. So this could be considered as a driving force of the reaction. Okay, so this is your Wolff rearrangement. But as you know, this ketene is not a very good stable species. Okay, that's why you cannot isolate this ketene. Generally you cannot isolate, but under special circumstances you can. So generally this actually ketene converts into the diketenes, but I am not going to form a diketene from here. And see, this is the general reaction. Now you see what this R could be. See, this R could be your alkyl group. Okay, and this R could be your aryl group. That means you may take your aromatic compound. Okay, it may your alicyclic group like cyclohexane, cyclopentane, etc., or it could be your say heterocycles. Okay, so any kind of the substitution could be there on this carbonyl carbon to give you the variety of the substances. Okay, so this is what. Now very quickly you can see the reaction actually. So in most of the time, guys, you will not you will not have actually this alpha diazoketone straightforward, but you may have certain other species which can actually produce this alpha diazoketone by the certain reaction. Okay, and most generally, right, most generally, so I am writing mechanism here, and generally you start this reaction either with the acid chloride or the mixed anhydride. Okay, so I am starting this reaction with the acid chloride. Say this is R C double bond O Cl, right? You have given this one, and then you have taken your diazomethane. Diazomethane means that means two of the hydrogen of the methane would be substituted with the nitrogen. So you can write it, write this diazomethane just like this. Okay, this is positive. And you know what would be the possible outcome for this particular reaction? So this chlorine along with the electron pair will grab this proton, and this will push this electron pair on the carbon atom, and that will result into this particular species. That would be your alpha diazoketone N2. triple bond, N I can write here, so positive, and of course this will have the electron pair, and you know this electron pair actually has come by the cleavage of this bond which is there with the hydrogen. Okay, so this compound actually intermediate you have formed. So this is actually your alpha diazoketone. This compound is known as the alpha diazoketone. Now this alpha diazoketone undergoes the Wolff rearrangement, and nitrogen will remove, and in that case 1,2 shift would occur. So what is the meaning of the 1,2 shift? See, if you give carbon number 1 to this carbonyl carbon and carbon number 2 this actually carbon which is electron rich, which is electron deficient, okay, and here actually the rearrangement would occur. So how the rearrangement would occur? You see, this R group along with the electron pair will join this particular carbon atom, and this electron pair would be pushed back between the carbonyl carbon and this CH carbon, and simultaneously this nitrogen will remove. Okay, so when this will happen, what you will have in that case? Okay, say nitrogen has removed, there is no problem in that, and your group has moved from here, so it will result in the ketene. And you know what is the ketene? Ketene is nothing, carbon double bond oxygen, and this is CH, and that CH would carry now this R. So again you can see this has shifted from here to here. That means this R will form bond with the CH. This I have formed already, and this will push here, actually this electron pair will push here. So this CH and this carbonyl carbon will be now doubly bonded. So this is, you can see the double bond is there, and this double bond is again there. So this is the ketene actually, and this you can call it as the 1,2 shift. This step you can call it as 1,2 shift. Okay, why 1,2 shift? Because the alkyl group which is which was present on the carbonyl carbon 1 actually has shifted to the carbon number 2. Okay, so this is the ketene actually. This is all about your Wolff rearrangement. Now if you see, if you are having your Wolff this ketene actually, so this ketene is the reactive species. It may react with the variety of the species. Okay, and when it will react the variety of the species like your nucleophiles, so you know the characteristic reaction for the carbonyl carbon is what? A nucleophilic addition reaction. Okay, so various kinds of the nucleophile can add to this carbonyl carbon to produce the different kinds of the products. So what are the possible products it can give? You can see here, say this was your ketene. I am writing this again, R I have given you, and then this was CH, double bond C, double bond O, right? This is your ketene. Okay, and that ketene may react with the water. If it reacts with the water, it will produce acid. Okay, and it may also react with the ammonia. When it will react with the ammonia, it will produce amide, and it may also react with your, say, alcohol. Then it will produce your ester. Okay, and this ketene may also react with your amines. Okay, and when it will react with the amines, it will produce N substituted amides. N substituted amides. Okay, so these are the possible reaction in that case. And one more thing which you should know actually, if I go back, see, you have seen this particular step where this alkyl group has shifted or from one position to position 2. Okay, this actually step is the concerted step. That means the bond breaking and the bond formation would occur simultaneously, and the nitrogen will remove. Okay, since it is the concerted step, the simple meaning is that whatever the stereochemistry is associated with this alkyl group would be retained in the product, as we have done in case of your Huffman bromamide reaction, in your Schmidt reaction, in your Lawson rearrangement, in your Ketenes rearrangement. All this this thing we have seen in all the cases actually, right? So in that case again the stereochemistry retention would be there. That means the retention of the configuration. This is the beauty of this Wolff rearrangement again. Okay, so now I can give you the various examples how we can form the different kinds of the product with this. Okay, so what I do, say I remove all these. I hope you have noted down this thing, right? And now what I am doing, I am taking first of all water to it. Okay, so this is your water molecule. Oxygen is having the 2 lone pair over there. So this can act as the nucleophile and can attack on the carbonyl carbon to produce this species. and then you will have here this species, which would be R CH double bond C O H H. This oxygen will have now positive charge over there, because one of the lone pair has been used in the formation of the bond with the carbonyl carbon, and this is your negatively charged species. So what can happen in the next step, guys? This electron pair can shift here, and that electron density can grab this proton, add this hydrogen as the proton, pushing back this oxygen hydrogen electron pair on the oxygen atom, and this will give you your product. Okay, so you can simply see your product would be R CH2 C double bond O OH. See, it has produced acid, and I already told you the ketene, when reacts with the your water, then it will form your acid. Okay, so this is one of the reaction. You should actually know this thing. Okay, then we can do the variety of the reaction in that case, and I'll explain a few important problems. Okay, and say what I am doing. I am taking this, say this example I am taking. I am having this CH3 CH2, this is CH2 again, and I am taking this acid. Okay, say suppose this you have given this species. Okay, and what you can do, you may actually write this reaction in that form also. The first species which you have been given here, oxalyl dichloride. Okay, so oxalyl dichloride is what? COCl whole twice. Say this is given to you. Okay, and this is given in presence with the triethylamine. Okay, so Et3N I am writing for this triethylamine. And second actually reagent which you have given is your CH2N2, which is your diazomethane. Okay, and then in the third step you have heated this system, and after that you have taken your ethylamine. Okay, so these reagents are there in the reaction. So what product actually you will form in that case, you have to identify this product. So from the basics of the organic chemistry, see, you have studied this organic chemistry throughout your BSc and MSc. Okay, so you must have an idea that this oxalyl chloride or oxalyl dichloride is very famous reagent to produce acid chloride from the acid. Okay, so in the first step what will happen, I can write my oxalyl chloride in that manner: carbon double bond oxygen, carbon double bond oxygen, one chlorine is here and another chlorine is here. Okay, so what will happen, this OH, the negatively charged hydroxide ion, would be replaced by the negatively charged chlorine. Okay, so I am not going to form the byproduct in that case, but straightforward I can give you this intermediate, which would be your CH3 CH2 CH2 C double bond O Cl. So this is nothing but your acid chloride, and you know this acid chloride when react with the diazomethane, so I can write here diazomethane, this is your N2. So what can happen, this HCl can be removed from here, and this electron pair would be pushed back here, and you will have your alpha diazoketone. So you can write your alpha diazoketone in that manner: CH3 CH2 CH2 again, this is carbon double bond oxygen, then your CH with this electron pair and your N2. So this is my way of writing N2. You can use different way also. Okay, this step actually we have done lots of time in the previous 4 reactions. Okay, and now what can happen, see, here actually you can do your Wolff rearrangement. So how the Wolff rearrangement would occur, if you heat that system, then 1,2 shift would occur. How 1,2 shift would occur, say this is 1, this is 2. So this alkyl group along with the electron pair will migrate onto this carbon, and that electron pair will be pushed back here, and that nitrogen will be removed. Okay, so when see, I can write minus N2 for this one here, and then you will have here ketene type of the species, and that ketene would be just like that: CH3 CH2, yet another CH2, which has formed with this which has formed bond with this CH, double bond carbon and double bond oxygen. Again I am showing this I am showing you this step. So this group along with this electron pair, this alkyl group, has migrated to this one. That means these 3 carbons has formed bonds with this CH. So CH3, CH2, CH2, CH, and this would be double. So this is double, this is double bond oxygen. So again this is your ketene. Okay, and now this ketene actually can react, this ketene now can react with the given reagent, and you know the reagent is actually ethylamine. So you can write EtNH2. Okay, so what can happen in the EtNH2? This can attack on this carbon and this will shift the electron density here, and then you will have your this species, that would be your CH3, CH2, and yet another CH2. Okay, and this is CH, double bond carbon. That carbon is connected with the nitrogen, and that nitrogen is having 2 of the hydrogens. Okay, along with this ET, it would be electron deficient now because it has used one of its lone pair in the formation of the bond, and this would be O negative. So in the last step, what can happen actually, this will come here actually, and that electron pair will grab this proton, pushing back this electron pair onto the nitrogen atom, and then you end up with the product, and that product simply looks like CH3, CH2, CH2 again, this is CH2, single bond C, double bond O, this is N, right, this is H, this is ET. So this would be product. So this is N-ethyl N-ethyl, see 1, 2, 3, 4, 5 pentanamide. So this could be your product in that case. See how easy these reactions are. Okay, so now what we can do, we can do other reactions in that case also. Say reaction number 2, you have been given this species, right? Okay, and after that, say this is your C double bond O, this is OH. Okay, so whenever you do these kinds of the reaction, always number the carbon atoms to avoid the mistake in the mechanism. Okay, and in that case guys, you have been given the reagents. First reagent is given SOCl2. Okay, and along with this triethylamine, and second reagent which have been given is your CH2N2 diazomethane, and in the third step you are heating the system along, and then you have taken this alcohol. Okay, so what would you expect actually? I already told you when actually you are doing the Wolff rearrangement and ketene is reacting with the alcohol, that means ester will produce. So definitely here in that case the product is going to be the ester, and I am not going to explain all the steps here, but I am explaining you. Say in the step number 1, this SOCl2 will react with this acid to produce the acid chloride, and SO2 and HCl would be removed as the gas, and this would be the driving force of for this particular reaction. That means in the first step you will produce this acid chloride. In the second step you have taken diazomethane, that means you will produce your diazoketone, alpha diazoketone you will produce in that case. Okay, so I am writing alpha diazoketone straightforward. Okay, okay, say beginners may have the confusion, so I am I am doing all the reaction. Okay, SOCl2, so this will give you the minus HCl minus SO2. Okay, this will liberate, and then you will have 1, 2, 3 double bond oxygen, and that would be Cl. Okay, and this will react with your diazomethane CH2N2. See, this is not actually, this triethylamine is not taking part, so it is used as the catalyst, you can say, or as a solvent in that case. Okay, and when this react with this one, okay, so what you end up with this, so you end up with this particular species, this double bond. Okay, and then CH N triple bond N positive over there with this lone pair. Okay, now the shift would occur actually. So how the shift would occur? This bond will cleave, this will shift over there, this will come here, and this will knocked out from here. So minus N2 you can write here. Okay, and then you have produced your ketene. So your ketene would be in that case this. Okay, and this has reacted with this CH, and this CH would form double bond carbon and double bond oxygen. Okay, so how many carbons were there initially? 1 2 3 4. So you have to have 4 carbons in that case again. Okay, so 1 2 3 4 5. Now but right now you are having the 5. Let's check whether we are having we were having the 5. Yes, definitely it will have the 5 because you have also added this CH2N2. So this is the correct structure actually which I have drawn. Okay, now this is ketene actually, and that step where actually you have removed this nitrogen in that case, this actually your Wolff rearrangement. So I can write WR for this one. This was actually Wolff rearrangement. Now you have taken alcohol, that means this CH3 CH2 OH. Okay, so this will attack on this carbonyl carbon to produce this species, and that species would look like 1 2 3. This is here actually. Okay, and say this is CH double bond C O H C2H5 with positive charge over there, and after that this would be negatively charged. In the final step, what can happen? This can come back and that electron will grab that proton, and this electron pair would be pushed back, and you end up with the product actually, and that product would be just like that: CH2 C double bond O O C2H5. So this is your ester actually. Okay, so this is how actually you can actually draw the products actually, right? So you see here what I am having in that case. So say this was carbon number 1, this is 2, this is 3, this is 4, this is 5. Okay, right, this is fine. So see, you can very beautifully forms the ethane in that case. Okay, there is no problem in that. You can understand this reaction very easily. Okay, now you can see a variety of reactions are there. You can go through the Google and do your practice, but some important aspect actually which I have to cover in that case, those aspects would be, say, ring contraction during Wolff rearrangement. Ring contraction, ring contraction. So what will happen in that case? If your starting material is having the 6-membered ring, so one carbon would be removed from that ring actually, right? And you will have the product with the 5-carbon ring. Similarly, if you have the 4-carbon ring, then you will have the more strained you have 3-membered ring. Okay, so this reaction can be used for the synthesis of the strained molecule, small ring strained molecule. Okay, but for this you have to have the alicyclic diazoketones. So how we can do such kind of the reaction? Say you are having this species. I am taking this example, and this example you can find in your Ketenes book. However, the mechanism actually is not there in the Ketenes book. So you have to be very careful in understanding the mechanism, but the reaction is given there. This is the species, this is your ketone, and that is your N triple bond N, right? This is positively charged species. Now if you carefully number this, say this is carbon 1, this is carbon 2, this is 3, this is 4, this is 5, and this is 6. So it's a 6-membered ring. Okay guys, it's a 6-membered ring, and if you do the reaction for this one, right? So you have already been given this alpha diazoketone. So you need to apply only the Wolff rearrangement. Okay, that means you are heating the system and you are doing the 1-2 shift. That means the carbon number 1 actually will break the bond, and that will shift to the carbon number 2, and the simultaneous removal of the nitrogen would occur. So how you can write this? You can see here I am cleaving this bond, and this whole part is shifting from here to here. Okay, there is no problem in that case. Okay, and when this happens actually, what you can do, you can remove this nitrogen from here. Okay, say you have removed this nitrogen from here. Now the important thing is that what will happen in that case? You see, since here actually you can see this species is given here, and this bond has already cleaved. Okay, so you will form a new ring actually, which would be 5-membered ring. Okay, and so how we can draw that 5-membered ring? Say this, 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 and this would be retained as such. Okay, and after that you see double bond carbon and double bond oxygen would be there. So if you number this, okay, so this was your carbon number 1, this is 2, this is 3, this is 4, this is 5. So what you have produced in that case, you have produced this ketene. So this is something very, very important which you need to understand. And of course your nitrogen will remove from here, N2. Okay, now it's an easy task actually, how actually you will put this double bond here. Okay, how you will put this double bond here. Okay, so see, already this hidden negative charge would be there in that case, and that hidden negative charge would form a double bond here actually, right? That will form the ketene. Okay, and this actually CO group will go to the terminal side. So it is coming at the terminal side. So you have produced this ketene here. Okay, so when you produce this ketene here, now the remaining thing is quite easy. Say now you are having your methanol, MEOH. Okay, say this is your MEOH. So what can happen? It can attack here, it can come here. Okay, and your next species would look like this. You will draw again a 5-membered ring, just like that. This would be double, this is C, this is O negative, and this is O H, and your Me. Okay, and in the last step, this can come here, of course positive charge. This will grab this proton, this will push this here, and then you will have your final product, and that final product would look like just like that. That would be your carbon, double bond oxygen, O Me. Okay, and if you number this, that means if you number this, this is 1, this is 2, this is 3, this is 4, this is 5. So you are ending up with the 5-membered ring with the production of the ester. Okay, so this reaction is very, very important, and you need to understand this reaction. Okay, for this actually you have to understand how the ketene formation would occur. So you can actually put some charges over there. Okay, and then you can draw this reaction. Definitely, you know, when this diazoketone will form in the earlier reaction, so this part will already having the negative charge actually. Okay, see, if you go back here, this was your alpha diazoketone, and in alpha diazoketone naturally this is having the lone pair actually, right? This had shifted here. So in that case also, this negative charge of the lone pair, when this will come here and this will grab, so this will shift over there. Okay, so what I can do, I can show this like that. Okay, so this is form this product. Okay, so this is how you can see, guys, this is very, very important and very easy things these are, and you can very easily form the different kinds of the products. Okay, now I can take one more example. Okay, in fact 1 or 2 more example to complete the reaction, to understand, to actually give you the better insight into the reaction. Say in that case you have been given this species, that say this is the benzene ring which is connected here. Okay, and this benzene ring is having, say, this is C double bond O, and this part, and this part, this is connected with the nitrogen, triple bond nitrogen. Okay, with a positive charge over there, and definitely when this will form actually, so this will have extra lone pair over there. Okay, so this you need to understand. Okay, and again you see the important thing is that this is carbon number 1, this is carbon number 2, so the shift would occur in that case, 1-2 shift would occur. So if you shine light on this case, that means the Wolff rearrangement is taking place, nitrogen will remove in that case. So how it will go? So this bond will cleave and this will shift onto this particular carbon, and this will remove from here, right? And sorry, I have broken the wrong bond, I need to remove this. Okay, this bond actually, right, this will break, and that electron pair will shift here actually. Okay, so now you have produced your ketene. So how you can write your ketene? It's quite simple, guys. See, this was your benzene ring. There is no change because retention of the configuration would be there. So however, this is not the stereo center or the any chirality is there, so you need not to worry about that. Okay, so when it is shifted, so you see here this was actually the how many number are there? Five membered ring is there. 1, 2, 3, 4 and 5. So when this bond is cleaved actually, and that part is shifted here, that means this reduction in the ring size would occur. Okay, contraction of the ring. So this will remain now as the 4-membered ring. So you will form a 4-membered ring here. So this is your 4-membered ring. Okay, and that 4-membered ring would have double bond carbon and double bond oxygen. You see, this has shifted. This has shifted here. This has shifted here. So this is double bond carbon and this is double bond oxygen, which would be outside the ring actually. Okay, so this is the 4-membered ring. Okay, and then this is formed actually. Okay, so it's straightforward what you can do, or if you want, then you can straightforward correct this one. 1, 2, 3, 4. Okay, 1, 2, 3, 4. So what you can do? You can do in that manner also. This bond will shift here, so this will convert it into, and that would be shifted here. So by any means you can do this one. Okay, so this is your ketene. Now this ketene can react with the variety of the reagents to give the different species. Let's say I am having ammonia in that case. Okay, so I am taking my ammonia. Okay, NH3. So it will add to it, and then your species would be, this is your 6-membered ring. This is benzene. This is your 4-membered ring. This is carbon. This is double bond oxygen. This is nitrogen, NH2 with positive sign, and 1 hydrogen is there, and of course it is negatively charged. This will come here, and that electron pair will grab this hydrogen, and this will be pushed back over there, and then you end up with the product, and that product would look like, see this, right? This is single bond, and now this is C double bond O. This is NH2. So you have produced your amide in that case. See how easy these reactions are. Okay, but if you take say in that case, if you take say methanol, MEOH, so you end up with the ester. No need to worry. Straightforward, you draw this, you put this, okay, and then C double bond O, O, Me. This would be the product. Okay, so this is how you can do the variety of the thing. But the important thing is that this have to be remembered actually, since this bond is cleaving from here. Okay, so and this bond actually, this part will be now freed. That means it will go to the terminal side. When it is going to the, see earlier it is the part of the ring, but after the cleavage of this bond, it is going to the terminal side. That means of course the reduction of the bond length would occur. Okay, so in that case you will have this particular product. Okay, I hope actually you are understanding the things quite nicely. So last thing which is left in this particular reaction, which I am going to cover here, would be your say intramolecular ketene trapping. Intramolecular ketene trapping. Okay, the example which I am going to discuss is also given in the Carruthers book. Okay, the very famous books, actually it is the most important book for your CSA or NET in the gate examination. So that example is given there in that case, but again without mechanism. But I am going to, so I am going to give you the mechanism as well in that case. Okay, there is no problem in that. And then you see here how the reaction actually goes. Say guys, you have been given this species, say this is nitrogen. Okay, so I am writing this in that manner actually, right? Triple bond nitrogen, single bond CH, of course a lone pair is there, C double bond O, and then you are having this NH TS. So this is your tosyl group. I have explained this tosyl group in my earlier lecture, so I am not going to waste the time to explain the tosyl group. Okay, it's a better leaving group actually, right? But it is, in that case, it is not leaving here from here actually. Okay, but it is there in that case. And you have been given this particular species. So this is again alpha diazoketone. So when you are having this alpha diazoketone, because see, this is carbonyl, this carbon is the carbonyl carbon, this is your alpha carbon, this alpha carbon is having this substitution. What I forgot to put positive over there. One lone pair is already there. Okay, now what you can do, if see, you have been given this species, you have been given pH CO2 Ag. Okay, so what is this actually? This is actually your phenyl ring, C double bond O O Ag, positive and negative. So silver one for salt actually are used in that case, I have already told you. So straightforward you can go for your Wolff rearrangement. WR I am writing. So what will happen in the Wolff rearrangement? That bond will break and this part will shift onto this carbon atom. This will come here and that will removed from here, right? Driving force for the reaction. So N2. Okay, now you have formed your ketene. So how actually you will write your ketene? So I am writing this in that manner. Say I was having actually this TSNH, there is no problem in that, and this I am having, right, this is CH, this is double bond C, this is C double bond O, and of course this is having this. Okay, so guys, don't worry about this thing that firstly I have drawn this above and I am drawing this and the downside. So this will not make any difference actually. If this is a chiral center, this will be retained after the reaction also, because the step is the concerted step actually. So retention of the configuration would be there. So you have produced this species. Okay, so now what you can do in that case, right? So you know, this is your what? Nitrogen. So nitrogen is having the lone pair. That means this can act as the nucleophile. So internal nucleophile is already available to this. So if you number this system, say this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4 and nitrogen 5. Okay, so what can happen? This can attack onto this carbonyl carbon and this will shift here. The moment this thing will happen, you will have your product. So see, there is a easy way to write the product actually. So actually the ring formation is happening in that case. Okay, and 5-membered ring you will form, and that 5-membered ring, that means at position number 5 you will have your this N, this nitrogen. So you simply draw a 5-membered ring here. Okay, so how I can draw the 5-membered ring? This and this 5-membered ring I have drawn. I am putting nitrogen over there. Okay, and this nitrogen is having H and the TS, and definitely a positive charge would be there. Why? Because this lone pair has been used in the formation of the bond. Okay, and after that carbon actually, right, this carbon number 1. So you can number in any way actually, right? You can number in any way. Say if I am calling it as carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, this is nitrogen 5. Okay, so carbon 1 is having, you can see here, carbon 1 is having the single bond oxygen with negatively charged. So what you can do, you can straightforward write O with negative. Okay, and after that you can see here this double bond is having this double bond is there between carbon 1 and carbon 2. So you can straightforward put a double bond here. There is no problem in that. Okay, and you see here at this carbon number 4 you are having this group, this methyl group. Okay, which is actually alpha. So alpha means below the plane. So you can put this group as such. So there is no problem in that. See how easily you actually form this particular product. So in the final step, what can happen? This lone pair will come here, right, and that will grab this proton, pushing back this electron pair onto the nitrogen atom, and you end up with the product. That product would be your 5-membered ring with nitrogen here, and of course this will have the TS now, and this would be this and double bond carbon. So this, see how beautifully you have formed this particular product. So there are variety of the reaction actually in this Wolff rearrangement, but I hope actually these much of problems can make a sense and you can understand the problem. See, however, see, there is a problem in yours, I think in CSIR NET 2012 examination they have asked already a question from this actually, right? Say there may be the question in your gate in the previous years, there may be the question, say from this Wolff rearrangement, but I didn't check the CS gate and other examination. But I think this much of explanation is sufficient to understand the reaction completely. Okay, I hope you grasp the things. Okay guys, so that's it for today. But before signing out, please, if you are watching the video and you are understanding things, don't forget to like the video, and please subscribe the tetrahedron chemistry classes so that I can do the more good work for you guys. Okay, and please do share with your friends also. Okay, so that's it for today guys. Thank you very much.